Okay, I've unmuted.
And also the video.
And the video, right.
So just check again. So that's just the
Right. Sorry, I have less experience with Zoom.
I also had zero experience. I just started like 10 days ago. So.
Right. Okay, I guess
How could they hear you? Okay, good. Thank you. Yeah.
Should be fine now. Thank you. Okay, so hello everyone. My name is Yuri Kalnishkan. I'm from Royal Holloway, and I will be talking about a concept of predictive complexity. So this will be more of a survey talk akin to Marcus's talk yesterday. So I won't be presenting one story or one application, but rather a survey of some results. I will talk about two measures of complexity. One I call predictive, another one I call asymptotic. So here is some bibliography. I put some bibliography at the start. So this is a humble cold paper of 1998 where Wolfgang Watkins introduced a concept of predictive complexity. This is where it all started. And this 2015 paper is a survey paper I wrote for the first shrift of Alexei Chervanenko's, which sadly turned out to be posthumous. And it contains a survey of key results with further references. So please refer to this paper for more references. And in the discussion of asymptotic complexity, I will be following this 2014 paper. I should say that these papers are not recent, and I have not been working in this area lately. I'm gravitated more towards machine learning rather than algorithmic information. Well, I hope it will still be interesting. Right, first, predictive complexity. Well, predictive complexity is a generalization of Kolmogorov complexity motivated by the online learning scenario. Well, the topic of this talk is perfectly aligned with this symposium. It's about algorithmic information and learning, except that learning is online. And here is the online learning paradigm. So we have some kind of feedback loop. There is a strategy that makes a prediction, then it gets to see the actual outcome, and then it suffers loss. And I will formalize this by the concept of a game. So a game in this context just means an environment, the space of possible outcomes, what can happen. Well, that will usually be bits, or it will be some finite space. As a matter of fact, it can be generalized to non-constructive objects and infinite spaces, but I'm not going to go into that. And there is prediction space. Well, what predictions we are allowed to make. And the loss function, which is how we are assessed, how the quality of our predictions is assessed. And these three form a game, our environment. And so prediction strategy is, technically speaking, just a mapping of the history to a prediction. And given a strategy, we can calculate the total loss on a sequence. It's just the cumulative loss, sum of losses over t steps. Right, so if we had the best strategy, if we had an optimal strategy, we could have considered its loss as an ultimate measure of predictability of the string or non-predictability. Well, because loss is bad. And this would be great, but the problem is that we don't have an optimal strategy. And every strategy, well, is greatly outperformed by some other strategy somewhere. Just think of a strategy that, okay, if our strategy says something like more like 0, 0.2 0.2, for example, the opposite strategy will be saying 0.8. And for some outcomes, that will be better. Some strategy, well, every strategy is beaten by some other strategy. Well, we can actually have an optimal element, but to get an optimal element, we need to expand the set, and we need to consider the so-called superloss processes. And here is the definition. A superloss process is semi-computable from above, and the differences have to be lower bounded by the loss of some prediction. You don't have to get this prediction effectively. There is no need to have a function producing this prediction, but it just should be there. And a process should be semi-computable from above. And for a loss, for the loss of a particular strategy, we will get an exact equality because there is a prediction. There is a computable prediction there. If we extend the class of losses like this, then under some very general conditions, there will actually be a minimal element up to a constant. And this is predictive complexity with respect to the game, motivated by this game. Right, here I have a construction. It's actually quite interesting. So this is the, no, this is the explicit formula. Well, superloss processes. We consider this expression. It's easy to see that its lowest, it's minimal up to a constant, but it's much harder to see that it's actually a superloss process. We have this formula that the differences are complex combinations. So these are actually weights, sum into one, of something which involves, well, which can be bounded by loss. But can those gammas be combined into one single gamma, which we would need for a superloss process? And there is a definition in online machine learning which says exactly this, that the game is mixable if we can find such a prediction. And it's about, well, this concept comes from prediction. This is what we need to have to be able to merge predictions coming from different strategies. On this slide, I have a geometric interpretation. We need something called a super prediction. A super prediction is something which is, well, to the northeast of a prediction. So there is an illustration here of what the set of super predictions looks for a square loss. So the points on this boundary are possible losses that can be suffered in a square loss game, and points to the northeast are super predictions. And the condition of mixability means that if we subject this set to this, if we apply this transformation, then we get a convex set. So it's just convexity, or mixability is just convexity over a certain set. And with some analysis, it's possible to show that the square loss game and a logarithmic loss game are mixable, and they define predictive complexity. There is predictive complexity with respect to the square loss and to the logarithmic loss. Then, if you look at the condition of a superloss process for the logarithmic game, then after some manipulations, it reduces to the equation of a semi-measure on a tree. And that 2 to the power minus loss will be semi-computable from below. The conclusion is that logarithmic complexity we have defined is actually Km, known in the theory of Kolmogorov complexity, and, well, negative logarithms or negative logarithm of the a priori semi-measure. There are two, well, important facts about the derivative result, which Marcus mentioned by Peter Gage of the University of Boston, that it's actually different from the plain Kolmogorov complexity. This result is very difficult. That theorem is very difficult, and very few people know it. And there is another fact which is much more simple technically, that it's actually close to Kolmogorov complexity. But I think it has a very important philosophical and general significance. These two definitions come from completely different perspectives. So we have the ultimate predictability of a sequence, and we have the shortest program described in the system. Why should they be related? And they actually are. I think this is quite a remarkable fact, and I don't think I fully comprehend the consequences of this. Well, one certainly related fact is that logarithmic loss has some extreme properties. In a way, that's the ultimate mixable loss. It's certainly related, but I don't think I can explain this better. Right, so these square loss and logarithmic loss are two examples of losses which specify complexities. And here are two examples of loss functions which are not mixable. First is absolute loss, and second is the simple loss, which is 0, 1, mistake or non-mistake. But for absolute loss, well, it's not mixable, but the set of super predictions is still convex. And it means that we still can define complexity, well, even though it has to be up to the square root, not up to a constant, but up to the square root. Well, then on this slide, I have some selection of results about existence and non-existence of complexities. There are a few open problems here, a few things which I don't know. In particular, I would be very interested to know if there are, well, is there any ground between constant and square root? There might be, I just don't know. For convex bounded losses, we will get complexity up to the square root. But are there games that give complexity up to something higher and not up to the square root? I don't know. Right, and then, so this was the definition. Now I'm going to present some facts about these complexities. And these facts will be related to will heavily involve the concept of entropy. So here is the definition. It's a generalized entropy, and it can be defined as expectation as the best expected loss given a distribution on the outcomes. If we fix a distribution, then the best expected loss is the entropy. And if the game is logarithmic game, then this is just Shannon's entropy. For other games, it's something else, some kind of generalization. So how is it related to predictive complexity? Well, it's actually not so difficult to see that entropy is average complexity per element. So if outcomes are Bernoulli variables, then the limit of the loss per element is, the limit of complexity per element is this entropy. It's actually not too difficult to see once you know it. And this has interesting consequences. First, well, entropy defines entropy actually, from the entropy you can actually reconstruct the loss, or rather the set of super predictions. You can say that you can reconstruct loss up to some parameterization. And the consequence is that if we have two complexities that are not too different, then they has to be for the same game. If you have two complexity measures that are pretty close to each other, then it's actually the same game. And this is the same complexity. So for example, well, one may wonder, can we tweak a logarithmic loss function to get predictive, to get prefix complexity, for example? Well, no, we can't, because if we tweak the loss, it will be something different by linear and by a linear term. So logarithm is too small here. And another thing I want to discuss is the inequalities. So we have, when do we have this inequality between two complexities? We have this inequality for all sequences. Well, if and only if we have it on average. And then if and only if we have it for entropies. And if and only if one set of super predictions is actually a subset of another. So there is a simple geometric interpretation to this. And if we're interested in inequalities of this kind, then it's a question of whether we can move one set of super prediction into another by scaling and shifting it. Right, so another result I want to mention is the unpredictability property. For Kolmogorov complexity, we have the incompressibility property. So, well, one joke from my student years, right? If you are a boss in a software company and one of your employees comes to you and says, I have written a compression program that can compress every file by 10%, then fire him on the spot for incompetence. Right, there can be no such compression program. Mapping from original file, the mapping from the original files to the compressed files just won't be an injection. So there must be incompressible sequences. But then most of the sequences are actually incompressible. The compressible ones are exponentially few, and this can be shown by the following statement: number of strings, this smaller number of strings with complexity lower by, then the length just goes down exponentially. And a similar result can be shown for predictive complexity. But instead of the length, we need to speak of the loss over simple basic minimax strategy. So if we have square loss and always predict 0.5, then our loss will always be 1/4. And for most strings, we cannot do better than that. And it can be formalized precisely. Well, this involves the concept of conditional complexity. I don't want to go into details here. Well, to formulate it neatly, we need to know the length from the start. Well, if we want to formulate it in terms of the original complexity, there will be some logarithmic extras. But and so this is an equivalent of incompressibility property for incompressibility property for predictive complexity. Right. Next thing I'm going to talk about, just I want to say a few things about another complexity measure, which I call asymptotic complexity. So we have seen that for predictive complexity, we have a problem of existence. So it's quite difficult when it exists, when it doesn't. So let's kill off the problem by just slightly changing the angle. So we will be looking at not at individual sequences, but at sets of sequences. So we will consider loss per element of a strategy and take a limit. So let's consider something like this. Infimum over strategies limit over sequence length of the maximum of loss per element. Okay, so there are some steps required to make this definition a bit more formal. Some steps are pretty obvious. So for example, the language has to be infinite to make a sensible definition, otherwise there will be no limit. And it's possible that the limit does not exist. Then we need to consider upper and lower limits. So these are two different concepts. And finally, if we're talking about infinite sequences, then we can actually swap limit and maximum. We can take maximum of limits along the sequence. And that's yet more complexities. And the definition of asymptotic complexities actually creates a host or a huge, crowd of concepts. There is upper complexity based on the upper limit, lower with the lower limit, and there can be computable and polynomial computable versions if in this infimum we restrict ourselves to computable or polynomial computable strategies. And in the uniform, well, that was the uniform definition, and in the non-uniform definition, it applies to sets of actual infinite sequences. There we can define upper limit and then take the supremum. Right. So, well, this slide is aimed to just confirm my proficiency in LaTeX. So these are the relations between the complexity measures. They're actually all different. They don't collapse. And the question I want to ask, the question I want to ask about it. Okay, so suppose that we have a few games. So how are complexities between them related? In a way, that's an extension of the inequalities question I considered earlier for predictive complexities. How are complexities with respect to different losses related? And it's actually possible to have a concise characterization of the set we can get, of the set of tuples we can get. And the description will be in terms of entropy. The answer will be in terms of entropies. Right, this is some technical condition. So what I will say will be applicable to weakly mixable games, which includes mixable games and convex bounded games. Perhaps something else I don't really know of. Well, then first we consider the set of entropies, the set of tuples of entropies. Then we take the convex hull of that set. And then just, that's nearly the answer. That's nearly the answer. There is just a little bit extra which is needed. We need to take a closure in a lattice. So Rn, well, Euclidean space is a lattice with respect to component-wise minimum and maximum. And if we have some set, we can have its lattice closure, upper closure, or as total closure. So here is an illustration. So on the left, we have a set which is not a lattice, and on the right, we have an upper closure. If we want to have the full closure, we will need to get a tail at the southwestern end of this. And now, with this, I can formulate the results. So the set of, right, not pairs. Okay, I meant tuples of complexities can be characterized as follows. So we get upper closure. So for upper complexities, we need to take upper closure of the entropy hull. That would be the case of computable and polynomial complexities too. if we consider lower complexities with lower limits, well, you might expect that we would need a lower closure. No, we need the full closure with both details. It's a remarkable. It's some remarkable fact. And here is some illustration. So how this set is built in 2 dimensions for 2 functions. First, we build an entropy curve. Well, this is just the curve of values of entropy. Then we take the convex hull, and then we add the closure, and this is how we get them. This is how we get. This is the set of possible pairs of complexities of languages. Right, so I'm out of my time, and this completes my talk. So, well, some maybe final message that we can define complexity measures for the online prediction scenario, and this complexity, well, we will have different complexity measures for different loss functions, and analysis of them. In the analysis of them, the entropy will feature a lot. So it's largely about the frequencies, right? So the complexity of a sequence is to a large extent about the frequencies of elements in the sequence. This is what, this is one of the key conclusions I want to show you. Right. Thank you. Questions?
Next speaker.
Thank you.